Okay, so can I start the session?
Would you be comfortable to switch off your video?
Yeah, I'll be switching off my
So
video.
just a minute, madam. Is the photography okay? Just a minute.
Presentation is visible to everybody.
Yes, it's visible, sir. It's visible.
Okay, so today is the last session and I'm going to talk about quantum machine learning. I know this 1.5 hours is not enough for a topic like quantum machine learning. And I know the participants are from varied backgrounds. So I'll go very basic with uh, quantum machine learning. What is quantum machine learning? And if time permits, then I'll be showing you a bit of code uh, to help you understand it better. So I'm going to just briefly go through, very brief, with minimal mathematics involved. I'll go through the topic. So the topics here that I want to discuss is, because for quantum machine learning, we should know what qubits are and what quantum gates are. Then we'll dive straight away to quantum machine learning. And there are three basically. I haven't written three here. So there are two written and there is a third one. So I'll mention the third one. One is data embedding in quantum computer. And then there is a variational quantum circuit. And then there is a measurement circuit. So I think there has been an error. So I've missed out the measurement one. And then if possible, as I said, I'll be doing some Python coding. But before moving on to what all of this is, I want to briefly state what quantum machine learning is all about. We all know what classical machine learning is all about. So this diagram, the block diagram that you can see on the right, you can see CC, that is the type of algorithm is classical and the type of data is classical. These are the types. This is the particular type that we encounter every day. That is, the data we get is a classical data that is from a classical data set, and the algorithms that we run are classical algorithms. Then there can be quantum data and classical algorithms. So if this one, it's the quantum data and the classical algorithm. This I'm not going to talk about. Quantum data means data that is coming from quantum measurements. So let us say if you have a system of atoms or photons in different polarization states. So if you're trying to measure them, so the measurement or the data is coming from a quantum system and you're processing that data using a classical algorithm. So that is this part. Now quantum is, again, you're processing quantum data using a quantum algorithm. This is the future. This is the future. But today we are going to talk about this region. So primarily we are going to focus on this region. So this is basically a hybrid between classical and quantum. So its data is classical, but the algorithm that we are going to run it on will be quantum. So we are going to simulate it on a quantum computer, or you can run it in an actual quantum computer, whatever you want. So there are options. I'll be discussing those options later on. So we will be discussing this region today. So the data is classical and the processing unit, the algorithm, is quantum. So what data embedding over here means, it's a very, very important process in a quantum machine learning, that how do you encode your classical data into a quantum computer first. So that is the first step. You have to encode a classical data into a quantum computer. And once you have done that successfully, and that is the major work, to encode the data. There are various techniques. I'm going to discuss one today because again of the time constraint. So there are various techniques to encode classical data into a quantum computer. So once you have done that, you run a variational quantum circuit. Again, so that is parameterized quantum circuit. We all know what a parameterized function does in case of classical machine learning, and we'll discuss it a bit. So we'll see, and then finally the measurement step. So moving forward with the presentation. Now, the first thing, what is a qubit? Just to give you a brief idea, qubit is a quantum bit. It's the basic unit of quantum information. So unlike classical bits, zeros or ones, qubits can exist in superposition. And this is the most important part in quantum mechanics, the superposition. You cannot have superposition in classical computing or classical mechanics. Superposition means the qubits can simultaneously be in two states. That is 0 and 1. And that is what makes quantum computing different from classical computing. So there is a parallelism going on in quantum computing. So you say that what is the state of a qubit? The state of the qubit is psi. It's not 0 and 1. It is a superposition of state 0 and 1, where alpha and beta are complex numbers. So this is the relation that must be true for every such superposition. What does this mean? Modulus of alpha square is basically, if you try to measure the qubit, then mod of alpha square times you will get the qubit in state 0, and mod of beta squared times you will get the qubit in state 1. So basically, mod of alpha square and mod of beta squares are the probabilities of finding or measuring the qubit in state 0 and state 1 respectively. So again, it's very counterintuitive, but this is how quantum mechanics works. It's not about either a 0 or a 1. It's always both. So superposition is something in quantum computer. The first thing that you do is you create superposition states. And superposition, again, I should repeat because this is central to what quantum computing is all about. The superposition and the next word, which is, or the next phenomena that is very important, and that is entanglement. I'll not go deep, very much deep into what entanglement is, but I'll show you what entanglement is, how to entangle qubits. I'll show you. So superposition is, it's not either in 0 or in 1, it's in both. And if 100 people measures the qubit, if say 40 of them gets the qubit in state 0, it means that mod of alpha square is 0.4, that is 40%. And if 60% of the observers get the qubit in state 1, that means 0.6 is beta squared. So this is what I mean. Now I'll go down the vector representation. Again, in quantum, for understanding quantum computing or quantum machine learning, you need to be very well versed in linear algebra. Again, a very important portion of mathematics, which you need to be very well versed of. Now, in terms of linear algebra, in terms of vector, ket 0, this is called ket. This is called a ket representation. This is a ket representation. By the way, this is also called the Dirac representation. So this is the state of the qubit. So this is the state 0. And if you look at the diagram above, this is also called a Bloch sphere. I'll come to the Bloch sphere in my next slide. This is called a Bloch sphere. This sphere is called a Bloch sphere. And right at the south pole, let us say, you say the point at the south pole is represented by ket 0, and the point at the north pole is represented by ket 1. You can interchange them. Again, it's merely convention. So ket 0 is represented, again, it's a two-state system. Remember, it's a two-state system. There can be 0 and there is 1. So these are basically, these are called the basis states. Exactly the basis states like I cap, j cap, and k cap in the Cartesian coordinate systems. These are the basis states, and 0 ket is represented by 1 0, a column vector, and ket 1 is represented by 0 1. So this is going to be very, very important if you want to understand. So the two bases, these are the two bases, 0 and 1. So the two bases are 0, ket 0, and ket 1. Vectorially, the ket 0 is represented as 1 0, a matrix element 1 0, and ket 1 is represented as 0 1. So these are the vector notation, and these are called the ket notation or the Dirac notation. Now, what is any vector? And please remember, the radius of the Bloch sphere is 1. So the radius is 1 because remember, the total probability must always add up to 100%. This is the criteria that you should keep in mind. So the total probability also always has to be 1. So you can see this black arrow and this point on the Bloch sphere. This is a point on the Bloch sphere. And if you look on the Bloch sphere, any point or any vector on the Bloch sphere can be represented as psi. That is, it can be expressed as a linear combination of 0 and 1, ket 0 and ket 1. How much is ket 0 there? This is the amount by which ket 0 is there. How much is ket 1 in psi? This is the amount by which ket 1 is in psi. In fact, it's the mod square of these. So this is the Bloch sphere. I'm going to go in detail with the Bloch sphere. So this is what a Bloch sphere is. So the Bloch sphere is a geometrical representation of a single qubit. Any pure qubit state can be represented as a point on the Bloch sphere where psi is given by this. So this is what psi is. And what is theta? Theta, if you see, now if you look at the first, if you note the coordinate system, then this is my x-axis, this is y, and this is z. And if you look at this red vector, then the angle that it makes with the z-axis is theta, and the angle that the projection of psi on xy plane makes with the x-axis is phi. So this is psi in general. In general, this is psi. In general, this is psi. So any psi, if you know what theta and phi are, you would know what the state of the qubit is. The state of the qubit is given by this. I want to show you a very good animation on this, and let me just. Is the page visible to everybody?
Yes, sir.
Okay, so now look at this Bloch sphere. You can see the same equation that we have written. Now I'm going to change this angle. Now look at this point. Look at this dot. This is the blue dot right on the North Pole, and this is 0. This is ket 0, and the dot, if the point is on the South Pole, it is ket 1. Now look at this polar angle. Now if I do this, now you can see this, it's moving. This is the theta angle that I'm changing, and you can see psi is changing accordingly over here. And the azimuthal angle, if I change this, you can see this is the azimuthal angle, that is phi, that I'm changing. And if I wish to see my probabilities, look at this. The probabilities is again, so if this is the case, then 0.809 squared, you can see this is my alpha, and 0.588, this is my beta. So if alpha squared, that is 0.809 squared, if you square it, you will get the probability of getting a 0, and that is 0.655. And if you square 0.588, you would get a 0.345, which is the probability of getting a 1. Now, look at this. If I change this, you can see this. The probability of getting a 0 is 0.9 around. That is 90% of the measurements will yield a 0 bit, and around 10% will yield 1. And you can see, because this vector is very much close to the North Pole, so the projection to the North Pole is very high as compared to the South Pole. So I would like to explain this as keeping two magnets, a magnet right on the North Pole and a magnet right on the South Pole, and the magnet attracts these uh, state vectors. So if the state vector is very close to the North Pole magnet, maximum number of times you would get zero value. And if it is close to the South Pole magnet, then the maximum number of times you're going to get 1. Now, what happens if I keep it in the equator? Look at this. I keep it over here and I put it 0. Now look at this. If this is the state of the qubit that is pointing along the x-axis, now see, this qubit is pointing along the x-axis, then the probability of getting a 0 is half, that is 0.5, you can see over there, and the probability of getting a 1 is also 0.5. So if 100 people measure the qubit, 50%, 50 members would get 0 answer and 50 would get 1 for the same qubit. Please remember that. So that is what quantum superposition is all about. So I hope this demonstration is clear to everybody, just to understand what it does. Now let me share my presentation again with you. Fine. Is the presentation visible now?
Yes, sir.
Okay, so that is what the Blocksphere is. Now, quickly moving on to what quantum gates are, because we'll be needing this when we'll be constructing our circuits. So quantum gates are basically unitary operators that act on qubits. Now, in any computation, you want to manipulate your bits. In this case, you will be needing to manipulate your qubits. Now, how do you manipulate qubits? In this case, you are going to need gates. Like in classical computers, you have gates. In quantum computers, you have quantum gates. And the quantum gates, the basic difference, again, I would not go very deep into it because it will take a day long if I go for the discussion of what unitary operators are. The basic difference between quantum gates and classical gates are they are reversible. Quantum gates are reversible, whereas classical gates are irreversible. So quantum gates are unitary operators that act on qubits. They change the state of the qubits similarly to the classical logic gates, but they operate in a reversible manner. Now, there are very, yes, Dr. Om. Uh,
Uh, uh, Good afternoon, sir.
yes, good afternoon.
Sir, I have one query.
Mhm.
Sir, can you say that what is the advantage of using polar coordinates against Cartesian coordinates here?
No, the advantage is, again, you see, it is symmetry. So whenever we are trying to use this polar coordinates, it's the symmetry, because you see that I have mentioned in the equation that the total probability must be equal to 1. So, and if you see the coefficients alpha and beta, if you look at that, so I should go back just a second. Yes, this one. Yeah. So Now, if you look at this, and if these are my basis vectors, and if you remember that if I say that it's x r in a two-dimensional plane, if I say r vector is represented as, sorry, x I cap plus y j cap, if this is my representation, then this x, now you see the analogy is, this is my zero ket and this is my 1. And this is the projection, because if I project I cap to r vector, what I'll get is I'll get x in this case. So this is what I get, alpha over here. So now if I tell you what is this, x square plus y square. So x square plus y square is nothing but r square. And if you look at this, this represents a spherical symmetry. In this case, it will be a circle. But if you work in 3 dimension, it's going to be a sphere. So whenever there is a spherical symmetry, so it's always better to work in a sphere, because again, if you see this radius of the sphere that I'm talking about, this is unity. This is 1, because the total probability always has to be 1. Okay?
Okay, sir.
Fine.
Thank you.
Okay, so let's moving on. So these are some of the operators in quantum mechanics. Pauli matrices we call, the sigma x, the sigma y, and the sigma z. These will be acting as, again, the first gate that I want to introduce is the Hadamard gate. The Hadamard gate is h is equals to 1 over root 2, 1, 1, 1 minus 1. Now I ask you a very simple question, what this Hadamard gate does. This is basically, in terms of quantum mechanics, we call them operators. And operators needs operands to operate on. Now the Hadamard gate, if you apply the Hadamard gate on ket 0, please check this. So what I want you people to do is, I want you to calculate this square root of 2. This is the matrix 1, 1, 1 minus 1. And if you remember, ket 0, I told you in vector notation was 1, 0. So I ask you, what is this value? And if you do this matrix multiplication, so this is a gate that is operating on ket 0, that is my qubit, let us say. So let us say my qubit is in pointing towards the North Pole. This is my ket 0. And if my qubit is pointing towards the South Pole, this is my ket 1. And anywhere else, this will be a state psi, which is given by that equation. So if I apply this Hadamard gate on ket 0, what I'm getting is, I'll be getting square root, I'm writing it over here because of lack of space. I'll be getting square root 1 over square root of 2. I'll be getting a 1, 1. Do you all agree? Right? And what does this 1, 1 mean? It means that I can write it as square root of 2, bracket closed. I can write it as 1, 0, plus I can write it as 0, 1. This is what I can do. So what is Hadamard gate doing? This, if you remember, is ket 0. And this, if you remember, is ket 1. So what is Hadamard gate doing? Hadamard gate is creating a superposition. So if you see, then this is 0 ket. And if I apply the Hadamard gate on ket 0, it is going to create a vector which is pointing along the x-axis. That is, this vector is a superposition of this and this. So if you look at the coefficients, please look at the coefficients. The coefficients are, alpha is 1 over root 2 and beta is also 1 over root 2. This is what we have. So this is 1 over root 2 with ket 0, 1 over root 2 with ket 0, and 1 over root 2 with ket 1. So what is the probability of...
আপনি বলেন আসবেন আসবে
what is the probability of getting a ket 0? The probability of getting a ket 0 is half, because if you square this off, and the probability of getting a 1, ket 1 is also half. So what is Hadamard gate doing? Hadamard gate, if it acts on 0, it is producing a superposition of 0 and 1. So Hadamard gate, in other words, if you think about it physically, Hadamard gate, if you have a qubit, Hadamard gate is rotating the qubit 90 degrees. 0 qubit 90 degrees like this. So this is what a Hadamard gate is doing. So this is an operation. So this is a gate operation which is rotating the qubit 90 degrees. And it is very, very important. Hadamard gate is one of the most important gates because it creates linear superposition of qubits. And that is what quantum computing is all about. Now, in general, there are rotation matrices. Now, RZ theta is a rotation operator with a theta rotation along the Z axis. Similarly, RY matrix, RY gate is a rotation around the Y axis for the qubit. Wherever the qubit is, it is going to rotate the qubit about the Y axis by an angle of theta. Similarly, Rx is this. So these are, I have written down because I'll be needing this in the next slides. So very, very important. I want you all to note this down because we'll be doing a simple mathematics to understand the quantum machine learning algorithm. That is the variational algorithm, how it learns. So these are the three very, very important matrices. Other matrices are just, special cases of all these, but these are very basic general gate operations that you can do on qubits. So Hadamard gate is just a 90-degree rotation, creates a superposition. RZ, Rx, Ry rotates the qubit along the three different axes by an angle theta. And these are the operators. And by the way, how do you get this? How do you get them? You get them by this operation, e to the power of I theta by 2 sigma z. And this is where Pauli matrices comes very, very handy. Pauli matrices are spin matrices or spin operators. So I want to measure the spin operator along the Z axis. So this is the operator that I'm going to use. I want to measure the spin. You know that an electron, if I use an electron, the electron is going to have two possible spins. One is plus half and the other is going to be minus half. And the value, if you want to scale it properly, it should be plus h cut by 2. In terms of Planck's constant, it will be minus h cut by 2. So the eigenvalues of these operators are plus h cut by 2 and minus h cut by 2. These are the eigenvalues of these operators. So basically, these are operators. I want to measure the spin along the Z. I want to measure the spin along the Y. And I want to measure the spin along the X. Whatever I want to measure, these are the measurement operators. And using these operators, we get the rotation gates. Similarly, for R y theta, it should be e to the power of I theta by 2 sigma y. So this is what the rotation matrices are. So let us use them and see. So this is a very basic overview. Again, I said 1.5 hours is not enough. We can spend more time in with all of these. So, and I'll show you some things. So let's move on to the data embedding techniques. So these are the data embedding techniques. Now you can see there are three, basically there are many more. Now there are three ways. As I said, the first step to quantum machine learning is how do you encode your classical data into a quantum computer. So there are three ways: basis encoding, amplitude encoding, and angle encoding. I'm going to deal with angle encoding today, and I'll show you how to encode data. But before that, let me show you the overall structure of quantum machine learning circuit. And this is the circuit. Now here you can see that this is your input data. This is your input data. This is your input data. So your data is input and these are the qubits. And by the way, this means there are many qubits, n qubits lined up, so on and so on. So there are n qubits. So we have initialized all the n qubits to 0 state. Let us say we can do differently. There are many options. So let us say we initialize them to all the n qubits to 0 state. And we have this feature map. What does this feature map? This is the way to encode the data. So I'm going to deal with today. I'm going to tell you how to encode the data. So you input the data and you encode the data. This is the SX. This is the feature map by which you encode the data into your qubits. So you encode the data into your qubits. And then you have the variational model where you have the parameters theta, which you can tune in order to learn. Now, what is machine learning all about? The classical machine learning is all about finding a mapping for a given input and then for a given parameter, set of parameters theta. So what do? You have X and you have a Y. What do we try to find out in classical machine learning is we try to find out a mapping. We try to find out a function that maps X to Y. What is the function that is we try to find out by tuning the parameters theta. So let's say, so what we decide on this mathematically, what we call them a model. This is what we call. So if it is a linear model, then we say that Y is equals to some theta naught plus theta 1 X. This is what we say. So this is the linear model. We assume this is a linear model and we try to find out the optimum theta naught and the optimum theta 1 value that fits the data. So similarly, a quantum variational model also does the same thing. You give some parameters, you initialize some parameters in the circuit, and then so what does these do? The parameters operate on what does this function u theta do? This operates on these qubits. And on what factor does this depend on? It depends on these theta factors. Similar like this, it depends on theta naught and theta 1. So you tweak these parameters. So for a given theta, set of theta, you look at the output, you measure the output, and that is this part, the measurement. You measure the output, and classically, now this is the hybrid part, you find out the loss function, you define a loss function. So that loss function might be anything. Let us say your prediction is y hat and your actual value is y. So your loss function might be this, or there might be any other different loss functions. So this can be a loss function. So what you do is you define a loss function and then you optimize the theta, and again you change the theta and feed it back to the variational classifier. So this is what you do. This is very similar. This is very similar to the classical machine learning architecture. The only difference is this. First of all, the data encoding part in classical machine learning, you directly input the data. If it's a neural network or anything else, or a support vector machine or whatever it is, you directly encode or directly input the data. Here, the first thing that you need to do is you need to encode the data into the qubits. This is what I'm going to show you. So the first part is you need to encode the data into the qubits. And then the second difference is the model, the variational model in a quantum machine learning circuit, it is based on the principles of quantum mechanics. That is, there are the two basic principles that make it different is the superposition, which is not there in classical machine learning, and the other is entanglement. I'm not again going into the details of entanglement, but I'll show you what entanglement is. And it is because of these two, which has no counterpart in classical machine learning. This is a unique strategy to try out. Again, I repeat, superposition and entanglement, they have no counterparts in classical computing or in classical mechanics. So you can use these two, superposition and entanglement, to really find out a good model. Now, let me remind you of this. There is a famous paper on neural networks. It's called, what do you have in a neural network? In a neural network, you have some input layer, then you have a hidden layer, and then you have an output. This is what you have in a neural network, right? If this is what you have. So you have the nodes, you have these connectivities, you have the weights and all. So whatever, you have these. What does a neural network do? Again, it basically, mathematically, it learns this function f. So there is an input and there is an output. So it learns the function that maps the input to the output. This is what it learns. And again, there is a question that how many hidden layers do we need to use? How many neurons can we put in a single layer? Which is the optimized number of neurons? What is the optimized number of layers? Again, there is no specific answer to these questions, but it is well said that even with one hidden layer, a neural network can approximate any function. So it is called a universal function approximator. So basically what is said is why neural networks are so very popular is that it's a universal, they are claimed to be, it's a universal function approximator. It can approximate any, they say it can approximate any relation between the input and the output. Now look at a quantum machine learning circuit. They are exploiting superposition and entanglement. So quantum circuits are also claimed to be universal function approximators, and they claim that it can approximate very intricate relationships between input and output. Very, very complex relationships can be modeled using a quantum variational circuit. Very, very complex relation. So nowadays we are going towards big data. We have too much data. We have huge number of data in millions and lakhs and millions. We have data. The processing power is huge. Maybe the complexity of the problem is great. So with all these things coming into the picture, into the dynamics, people who are advocating quantum machine learning, they say that quantum machine learning or this quantum variational classifier is a universal function approximator. It can approximate any relation whatsoever between the input and output. And it is because of these two very important relations which cannot be mimicked by a classical computer, that is superposition and entanglement. So what is angle encoding? So coming to what angle encoding is, I think let me erase these inks. What angle encoding is, let's say you have a data. Now you have a data point X. X is, let us say 0.3 and 0.6. Now this is the first data point. And so I'm talking about two features of the data set. So there are two features. The first feature is 0.3 and 0.6. Now, first thing that you need to do is you need to normalize the data. Whatever data you have your standard normalization or standardization techniques in classical machine learning. So when you normalize or standardize the data, you can get them in these ranges. So let us say the first data point is 0.3 and the second data point is 0.6. Now, how do you encode this classical data into your quantum system? So how many features do you have? You need to decide how many features first. You have two features. So what you do is you take two qubits, both of them initialized to 0. So you take two qubits. Now you can select any. Again, you have the option. Let us say you select to rotate this qubit along the x-axis. That is the Rx matrix that I was talking about. By the amount. Now, what is the amount by which you want to rotate? The first data value, that is 0.3. Let us say you want to rotate the second qubit along the y-axis. That is, you want to manipulate it along the y-axis. And what is the amount by which you want to rotate? And the amount is it's the second data value. Let us say you have a next data point, minus 0.7. This is the third feature. of the first data point. Now you'll have 3 qubits. And let us say you wish to rotate it again by along X. And so you rotate it by this. So this simple logic, that is angle encoding. You understand, you encode the data as the rotation angle to the qubit that you have initialized. So this is the basic logic, a very simple logic. So how many qubits do you require for this? You first have to decide how many features are there. And then you'll have to add on these qubits. And for all these qubits, for every single qubit, you will put the data. So the first data goes here, the second data goes here, the next qubit, and so on. So this is how you encode it. Now let me show you this. Just a second. Is my screen visible to everybody?
Yes, sir.
Okay, so this is a quantum circuit simulator. You can see this. Now here, if you'll watch, then these are the measurements, the yellow ones. And here you have all the gates that you can do. Here are the qubits. Let us say if you don't require a qubit, you can delete these qubits. So this is what you have. So let us say, I want to show you something. Let us say I put this Hadamard gate over here. And I have this Hadamard gate over here. Here there is a code written over here. And if I want to only measure qubit 1, so I have switched it off, and this is qubit 1 that I want to measure. Look at this graph. This is the histogram of measurements. So you can see counts 50. So 50% of the time, if you measure the qubit, you will get a 0. And 50% of the time, if you measure the qubit, you will get a 1. So that's the measurement because it was initialized to 0. And remember, Hadamard gate puts it into a superposition. So this is what you have. Now I want to show you a simple entanglement case. This is called a CNOT gate. I don't want to go into CNOT gates, but again, so this is a CNOT gate and I switch this on measurement. Now these two qubits are entangled. What do I mean when I say entangled? You see the measurement output. You see there can be 4 possibilities. What are the 4 possibilities? The 4 possibilities is there are 2 qubits. It can be 0, 0. It can be 0, 1. It can be 1, 0. And it can be 1, 1. But if I create this circuit and I measure both the qubits, qubit 1 and qubit 2, what is the histogram that I'm getting? The histogram I'm getting is I'm getting a histogram of 0, 0 and I'm getting a histogram of 1, 1. There is 0 probability of getting 0, 1 and 1, 0. What does this mean? It means that if the first qubit is 0, then the second qubit will also be 0. And if the first qubit is 1, the second qubit is also 1. So in other words, we say that the qubits are entangled with each other. So a very simple way to entangle qubits is you apply a Hadamard gate to the first qubit, and then you apply a CNOT. CNOT, by the way, it means controlled NOT. Controlled NOT means whenever this qubit, that is the first qubit, is called the control qubit and the second qubit is called the target qubit. So if the first qubit is 0, do no change to the target qubit. And if the first qubit is 1, then swap or put a NOT gate to the target qubit. So this is what CNOT does. So if you apply these 2 operations in the serial that I have shown, you will be creating an entanglement. So I'm going to show you more of this. So let me return or share. Okay. Is my Jupyter notebook visible to everybody?
Yes, sir.
Okay, fine. So you need to, I'm going to work in two libraries that can be easily installed in your system. And both are for working in quantum machine learning. One is called Qiskit and the other is called PennyLane. So I'm going to show you this data encoding part in Qiskit first. So see, these are the libraries that I want to import. Now let me tell you, this is the quantum circuit. The AER is what is Qiskit. Am I audible to everybody?
Yes, sir. Audible.
Is it visible now, everybody,
Yeah.
properly?
Yes.
Okay, fine. So what is this AER? This AER is basically a simulator. So now here, sitting here, I may, yes, if I log into some IBM website, quantum computing cloud services, I will be able to use actually a quantum computer. But here I won't be using an actual quantum computer. I'll be simulating a quantum computer. So you can simulate your programs in a quantum computer rather than running them actually on a quantum computer. Because again, if you want to actually run them in a quantum computer, you'll be queued. So there are very few quantum computers right now available, and there are many jobs that are pending. So maybe after 5 or 10 jobs that is done, you will be your program will be run in an actual quantum computer. So we won't wait for that. We will be running it in a simulator. So basically, AER is a simulator for Qiskit. So this is I'm going to uh, import all these libraries, and all of you, if you want this code, again, this code is already available. If you want this code, I can share the code. So look at this quantum register. We want two. So you can see there, we want two qubits to be there. So this is one. And we want a quantum circuit to be built, and we call the quantum circuit QC. And look at this, apply quantum gates, and I apply a NOT gate. Let us say X is the NOT gate. Now, if you go back to my slide and if you look at the Pauli matrices, and you will see sigma X was basically a NOT gate operator. It was inverting it. So if you put a 0 bit to X, it will make it 1. And if you operate X on 1, it will make it 0. So X, QC dot X, simple. X is the NOT gate. And which bit do you apply on? This is the quantum register. You apply it on the 0 bit. And I want to run this. And if I want to draw this, you can see this. Very simple. You can see this is this bit 1. And you apply a NOT gate, and this is what you have. Now I want to encode my data. I gave you the angles. Let's say I name them angle 1 and angle 2 is 0.6. So what I want is rotation. Here you can see simple Rx rotation. And by what angle do I wish to rotate? I wish to rotate it by angle 1, which is 0.3. And which qubit? 0. This qubit. And I want to rotate the second qubit by along the y-axis by an angle of angle 2, which is 0.6. So I apply this and I simulate this. So I need a simulator. So I need a simulator. So the simulator is here. You can see AER state vector. I want to get the state vector. That is, I want to get what the state is. So let me run this and I want to draw this. So look at this. First, look at the diagram. This is my diagram. So here you see for the first, you apply a NOT gate and then you apply an Rx rotation of 0.3. And in the second, you apply this. Now you can do anything. You can do anything to encode 0.3 or 0.6. It's not necessary that you need to apply a NOT gate. You can apply a Hadamard gate. You can apply anything else. You can or you can omit this and see. So anything, but these data has to be there, 0.3 and 0.6. These are the data that has to be there. So if I wish as simple as that, I want to have 3 qubits. So what I'll do, I'll have 3. Now look at this. I'll have this. So this is what I want. And if I say I want to have an angle, a separate angle, let's say an angle equal to minus 0.7. And I wish to have this, let's say, on the 3rd qubit. So this is what angle 3 is not defined. Let's see. Oh, this is angle 2. This is angle 3. So let me run this again. Yep. So you see this. So this is what you have. This is what you have. So you see the circuit, and this, I'm getting the state vector. I'm getting the state vector. That is what is the state of the final output. If I do all these operations on these qubits, what is the output? This is what I'm getting. Now I'm going to make things simple. What I'm going to do is, let's remove this. Let's go back to the previous one, because I can, this would be simple to do. Yeah. So I get this again. Now I want to show you something. I think this is already open. Just a second. So what have I done? Please look at this. I have applied a NOT gate in the to the first qubit, and then an Rx of 0.3. And to the second qubit, I have applied an Rx of 0.6. So I can go and simulate the same thing over here. That is, I remove this. I remove this. So what I do is I apply a NOT gate here. Then I apply an Rx gate here, and I apply an RY gate over here. Now I wish to tweak this. So you can see here in the program, RY pi by 2 is written. So what I'll do is I'll put a 0.6. And Rx is written pi by 2. So I'll put a 0.3. So this is what I'll do. Now the same, you can see the output. Look at this. Look at this. This is what you get. The probability distribution. This is the state vector. Look at this state vector. 0, 1 is around 90% probability. So now if you measure the state, you have prepared it, your circuit, you 90% of, more than 90% of the time, you will get the state of the 2 qubits in 0, 1. 0, 0 is very small. You can see 1, 0 is again negligible, again almost 0, and this is almost this. So now if you go to my this, now look at the state vector printed over here. I told you these are the coefficients. These are the coefficients that I am getting. So it is 0, 0. You can see these are the 2 coefficients that I'm getting. So there will be 4 coefficients, and mod square of those 4 coefficients are going to give you the probability. So if you look at these mod squares, you can see one will be more than 90% and the other will be around this square of 0.29 and something like that. So if I go to this again, sorry. Yeah. So you can see this. Now I can show you another one where you can exactly see this. go there. Now you look at this. I have a NOT gate. I have an RX gate, and I have an RY gate. And now I change this RX to 0.3 rotation, and I change this to 0.6, and I get this. Now look at this. These are the four states. Now look at this. Please look at this. 0, 1. What is the value? The value is 0.94461 plus 0i. And if you look at this 0.944610i, look at this 0.94461 around, and this 0i. You can see this. And if you look at the second one is the amplitude of 0, 0. You can see the 0, 0 amplitude. It is minus 0.14276i. You can see minus 0.1427637. J here means the imaginary iota. So you can see exactly all of this over here. So these are the simulators that you have. You can simulate them and see. So you can play around with these. You can change the rotation angles. You can apply whatever gates you want. Let's say you wish to apply the Hadamard gate also to this. Now you change it, and you can see the probabilities are changing. And I can go to this one, and I can show you how the probabilities are playing. So I can apply a Hadamard gate in between, and look at this, the probabilities. See, the probabilities have changed, the histograms have changed. I can apply a C naught over here, do some entanglement, and this is what the entanglement is doing. Now you can see again the probabilities are changing. So this is what you can do. You can do whatever you want, but the main part is RX and RY. These are the coding parts. This is where you encode your classical data into the quantum computer. So the first thing, you need to feed your data, your classical data set, into the quantum computer, and this is how you feed the data. So this is one part. So I'll be moving on to the next one. Right. So let me, yeah. So I think, is the presentation visible now? Fine. So angle encoding, I have mentioned it. Now, if you have the next data point, look at this. This is the first data point. This is the first data point. So you have three features. You have three features. X naught. This is the first data point. So this is your just a second. Yeah. So this is your X naught. X naught has three features: X naught 1, X naught 2, and X naught 3. And you have the next data point, X1. You have X11, X12, X13. So this is feature 1, this is feature 2, this is feature 3. Now this is the second data point that you are encoding. And you can choose different rotation axis in which you want to rotate. You want to encode the data. So if you have the next data point X2, you'll have another one. So this is how your circuit will progress. So this is how you encode your data. So the next and the most important part is, how do you optimize the circuit? Now I'm going to give you a very, very simple example to optimize the circuit. Yeah. Now look at this. This is 0. Now I want you to do the maths. The maths is simple, and you can do this maths. Again, very simple mathematics. So ket 0 is 1, 0. This is the vector notation. Sigma z, that is, I want to measure the expectation value of the spin up, the spin along these two axes. So if this is my spin up, that is the z axis, this will be spin down. So that is, I want to measure this. I want to measure this. So And why this expectation? Because again, remember in quantum mechanics, you don't have a single outcome. You can have different outcomes. Different people might have different outcomes. So what you can take from a quantum measurement is you can take the average of all those measurements. And average of measurements is said the expectation value of this. So you want to measure the average value of the spin of this qubit, along the z-axis. So remember, the z, sigma z, is this matrix. And if you look at this matrix, then it has two eigenvalues, eigenvalue 1 and -1. And what are the eigenvectors corresponding to 1? Corresponding to 1, it is 1, 0, that is ket 0. And corresponding to -1, it is 0, 1, that is ket 1. This is ket 1 and this is ket 0. So this is sigma z. Now let us say, very simple, let us say my state is in sigma. My state is in 0. So my qubit is already pointing to the positive z-axis. So it is not in superposition state. It is in pointing towards the z-axis. Now I want to measure the spin along the z-axis. What will be the expectation value? What expectation value do you think? What will be the average value? Because the qubit is pointing towards the positive z-axis, it is not in the superposition. Every observer will measure the same eigenvalue, that is 1. So every observer will report that it is in state 0. That is, look at this. So if this is sigma z, what is sigma z? I want to calculate this expectation. When I say expectation of sigma z or any operator, I mean that it has to be expectation on the state. This is the notation in quantum mechanics. And this is what we call the measurement. That was the final part, measurement. So I want to measure. Now, what is psi in this case? My psi in this case is ket 0. This is my psi. So I want to do this. I want to sandwich the operator between the two state vectors, and I want to measure the average value. So this, by the way, this is called the bra. This is called the ket 0. This is called the bra 0. This lives in the dual space. And what it does is, in mathematical terms, it is just the transpose of this. So if this is a column matrix, this will be a row matrix. So 1, 0, you can see 1, 0 is ket 0. Sigma z is this matrix. And 1, 0 is if you transpose that. And if you compute this, I want you to compute this. If you compute this, you're surely going to get the value of 1. As simple as that. So what does this mean? It means that if you already have your system in the 0 state, that is pointing up, and if you are measuring the spin along the positive z direction, every observer will measure it as ket 0. So what is the eigenvalue of ket 0? The eigenvalue is 1. You can see from the matrix, the eigenvalues will be 1 and -1. So this, you will get the value to be 1. Now, if I ask you a very simple question, if I did a Hadamard gate, and then I measured sigma z, what do you think should be the expectation value of sigma z? Remember, Hadamard gate does is it rotates this vector and points it to the positive x-axis. So now this is like this, a 90-degree rotation. This is what a Hadamard gate does. So if you remember, now the psi function, the psi state will be 1 over square root of 2, 0 plus 1. It will be a superposition of these two. And if you wish to write it in column vector, it will be 1, 1. This is what your state psi is. Now, this is your state psi. It is no longer ket 0. It is ket psi. Now, if you wish to calculate this now of sigma z, I encourage you to calculate it, and I'm sure you will get a value 0. because half of the time people would say that it has eigenvalue +1, and half of the time, because if it is in this state, half of them will measure it in the positive z direction and half of them will measure it along the negative z direction with an eigenvalue of -1. So half people would say it is +1 and half people would say it is -1. And so if you take the average, you will get a 0. And if you work out the mathematics, you will see that instead of taking 1, 0, if you take 1, 1, 1, 0, 0 minus 1, 1, 1. I keep aside the 1 by square root 2. And if you calculate this matrix multiplication, I'm sure you will get a 0. So this is what the measurement does. This is what the measurement does. As simple as that. So if you apply a NOT gate after the qubit 0, what does the NOT gate does? The NOT gate makes it 1. This is a NOT gate. It flips it. So if you have a qubit pointing to the north pole, the NOT gate, after the NOT gate operation, it will rotate it by an angle of pi and it will point along the south. So it will make it 1. 0 will be 1, 1 will be 0. Now, if you measure this sigma z, every person that will be measuring sigma z will be getting ket 1 because it is in ket 1. So what is the average value? The average value will be -1 because the eigenvalue for ket 1 is -1. So the measurement outcome, the expectation value will be -1. So this is what you will expect. So this, if it is 1 sandwiched between 1 and 1. So if you calculate this, you remember ket 1 was 0, 1. If you remember this, ket 1 was 0, 1 and bra 1, that is the transpose, will be 0, 1 of this. And if you sandwich this matrix of sigma z, you will get an eigenvalue of -1. This is what you'll get. So this is very simple. Now, what I want you to do is, I want you to do this this is what we were doing in encoding techniques. But if I go back, now once your data is encoded, please, I want to go back. I want to go back. Sorry with this. Look at this. This circuit. I am talking about this part now. This is the part. This is done. You have encoded your X. You have encoded your X, your input data. Now it is the training part, the variational model. That is the parameterization part. You'll change the parameters and you will achieve your goal. So this is the variational part. So I'm talking about the variational part, that is U dependent on theta. So now let us say, yes. Now let us say this is what you have. Let's say you have two operations, Rx theta 1, Ry theta 2. That is, you first rotate, you initialize your bit in this or whatever. After encoding, this might not be your state. After encoding your classical data, this might not be your state. It might be something different. But I'm giving you a very simple example. Let us say this is your state. And if you operate this, after this, you operate or you apply this gate, Rx gate, an angle of theta 1. Now, theta 1, these are the parameters. Theta 2, these are the parameters. Like in your model, y is equals to theta naught plus theta 1 x. So these are your parameters in your models. In neural networks, the weights are the parameters which you tweak, which you change. Similarly, in the variational part, which I said u theta, these are the parameters that you tweak. Now let us say you first apply the Rx, you rotate it by theta 1, then you apply a y rotation rotated by theta 2, and then you measure the expectation of the Pauli matrix. Now what is Rx and Ry? I have put it for you. Rx and Ry is this. I've already written down it in my first slide, in the previous slide. Now this is another slide where I have written for you explicitly what is Rx theta 1. Now this is what you remember. You remember Rx theta 1 was e to the power of I theta 1 by 2 sigma x. You remember this is the Pauli matrix. So you get this matrix. And Ry theta 2 you get this matrix. So what I want you, and sigma z is you, we know all of this is this. Now 0 is this. Now what I want you to do is first apply this on this, then apply this on the result. What do you get? So this is what I want. So here is the state psi. This is what I want to mention. This is the state psi at this point. At this point, the state is psi. After application of Rx on 0, then application of Ry on the result, you get a state psi. So you apply Rx on 0, you apply Ry on the result, and you get psi. So what I want you to do is, I want you to do this cos theta 1 by 2 minus I sine theta 1 by 2, blah, blah. That is my Rx on 1, 0. That is 1. And then I apply again cos theta 2 by 2 minus sine theta 2 by 2 and blah, blah, this. So this matrix, and you calculate what you get. So you will get psi. And whatever you get psi, you will get a 2 by 2 sorry, 2 by 1, 2 cross 1 column matrix. This is what you will get for psi after multiplying. So what is the dual of psi? That is the bra of psi. The bra of psi will be the conjugate, the complex conjugate of this. So it will be a 1 cross 2. What I want to do is, I want you to calculate the measurement. Now you do the measurement. What do? You calculate the expectation value of sigma z. That is, I want you to calculate this sigma z psi. This is what I want. So I want this matrix column that you have for bra of psi. You have a sigma z, which is a 2 by 2 matrix. And then you have a ket of psi, which is a 2 cross 1 matrix. So you do this matrix multiplication. I encourage you to do it. And please check. Just a second. Let me erase this part only. Yep. And I want you to see, you will get this result. Very, very important result. So what is the expectation? The expectation, that is the measurement that you are getting, is dependent on theta 1 and theta 2. That is, the measurement of sigma z, or whatever measurement that you are getting, is a function of the thetas. That is what you are getting. This is the function of the thetas. So this is what you're getting. So this is your outcome. This is the outcome of your variational circuit. This is f theta. Now you can apply any classical optimization techniques to optimize theta. So that is, the next step is, what you do is you define a loss. Your loss is your actual y minus your outcome, whatever your measurement is giving. Let us say, this is one way to define loss. There are many other ways. And if this is your loss, you define the loss and you apply any optimization, classical optimization techniques, that is gradient optimizers or non-gradient optimizers. There are many. You can apply them and you can minimize your loss and you can find the optimal theta values for which the loss goes to minimum. And this is how you train the model. So the basic difference is the way in which you are creating the circuit. You are creating the output. Your model, this is the basic difference. Your model. In classical machine learning, your model was very well mathematical models, well defined. The equations were very well defined mathematical models like linear or polynomial or whatever it is. In this case, these are the gates or the rotation that you do on the qubits, and you play around with whatever you want. You can make it as complex as you like. Understand this. You can repeat this step as many times you like. Now, if you want to have many more parameters, you apply another gate. Let's say you want a third parameter to be involved. So you apply again you apply this like RZ theta 3. It is very simple, like classical machine learning models. Let's say you have a data set. Do you want to model it with a linear model, or do you want to model it with a quadratic model? Then you will have another parameter. You want to model it with cube. So you're increasing the parameter, by which I mean you are increasing the complexity. Here also, if you are adding more parameters, you are increasing the complexity of the model. So you can increase by whatever amount you like. Just a second. Right. So this is how, so this is a function. So this is ultimately what you get out of u theta. So by all of this, what I'm trying to say is, so this is finally your thing. So this is u theta. This is nothing but your u theta. So this is how you parameterize the circuit. You do apply rotations by different angles, and then you change those angles, you update those angles based on the cost. So you have your this is your measurement. This is your measurement, which is this. In this case, a very simple example. Now you do more complex operations. This output, that is expectation values, will be very much different. And then you compute a cost. You define a cost. What do you mean by a cost? And then you update it by any regular optimizers that you have. So I'm going to show you this in a code. So let me show it to you. Fine. So here I'll be using PennyLane because again, embedding techniques are, it's easier to understand in Qiskit, and the variational circuits are easier to understand in PennyLane. So I'm going to show you both. You can work in both PennyLane and Qiskit. In fact, the final data set that I've worked on, heart disease prediction data set, I'll show you the data set. I'll show you the programs. I have done both. I have done it with Qiskit and I've done with PennyLane, and I've done a classical classification classical machine learning classification also, and so that we can compare them. So, but for the time being, I want to show you this simple variational circuit. So let us run. So you are importing PennyLane SQML, and please remember, NumPy has to be imported from PennyLane if you're working with quantum machine learning. Your regular NumPy won't work. So you'll have to import it. Now, this is the device that we are creating. As I said, in Qiskit, you had to create a simulator. Even in PennyLane, you are creating a simulator. And this simulator in PennyLane, we are choosing a simulator. You can choose from many simulators. You can go to the PennyLane website and you can see there are many simulators. So we are choosing the default qubit as our simulators. So the device is QML device. So, and wires are 2. So we are using 2 qubits. So these are 2 qubits. So, and I'm naming it as my device dev. So construct a Q node. Now, what is a Q node in this case? The Q node is, the device is being connected. You create a device. You see, you create a device. You create a device. This is your device. DEV is your device that you have created. That is your simulator. And then you create a circuit. Now you see, you create a circuit. I told you in Qiskit also, we created a circuit. Now you can see here, you are applying Rx rotation. And by what angle? It is params 0. Which qubit are you applying it? You're applying it to qubit 0. RY rotation, the second parameter you're using, you're again applying it to qubit 0. The third parameter, an Rx rotation, you're applying it to qubit 1. And again, I'm doing a C0 between wire 0 and 1. And what is returning? What is the circuit returning? The circuit is returning the expected value of Pauli Z. You can see. And on which qubit? Qubit 1. The first qubit, not qubit 0, qubit 1, let us say. So this is our circuit. This is how I am defining the circuit. So what is Q node doing? Q node is attaching the two. It is attaching the dev, that is my simulator, with my defined circuit. This is my defined circuit. So my circuit is now attached to the device via this command. So the device is the default qubit. You can see the default qubit. This is my device. So it is attached. Now if I run, now I define the parameters. What are the parameters? This is, see, this is theta naught, theta 1, theta 2. These are my parameters that I am defining. So these are the parameters I can tweak, I can change. So the initially I am defining the parameters. And if I draw the circuit, please note, this is what you have. So for the 0 qubit, you can see there is an Rx and Ry, and 1, there is an Rx. So you'd see my circuit. There is an Rx and Ry to wire 0. And there is an Rx to wire 1. And then there is a C0 between wire 1 and 0. So there is some kind of an entanglement. So I've also done an entanglement between. So this is my U theta circuit. This is not my data encoding part. Data encoding is done. This is my U theta circuit. And this is my measurement on qubit 1. So now this is my parameters again. Let's say I define my parameters. Maybe this is repeated, but whatever. Now I want the circuit to return the value. What is my circuit returning? You see, my circuit is returning the expected value of the Pauli Z. Again, that expectation value. So it's returning 0.605. Now what I do is I define a cost function. Let us say, simple. I'm doing very simple things. I define a cost function. My cost function is 1 minus the output of the circuit squared. So my output of the circuit is 0.605. And this is, I could have done anything. I could have done 1 minus circuit, or I could have done simple circuit X, the output of the circuit as my cost. So I define my cost function like that. And let us say this is my initial parameters. So you need to initialize your circuit first. Even in classical machine learning, you have the initial parameters and then you iterate it. So this is the step. So we initialize the parameters and you optimize the cost function using gradient descent. This is the classical simple optimizer. You have gradient descent optimizer in PennyLane also. So PennyLane, you have imported it as QML, and the step size, you can change the step size, you can change the number of steps. So this is what I'm going to do. And I'm going to iterate, and I'm going to show after every 5 steps. Here you can see. So it is all done every 5 steps. You can see the cost after the step. So cost after step 100, you can see this is the cost. So it has been almost reduced to 0. This is almost reduced to 0. You see, at the start, the cost was this. At the start, the cost was this. If I initialized with these parameters, but with 100 steps, the cost is reduced to almost 0. And these are the optimized rotation angles. You remember theta naught, theta 1, and theta 2. These are the optimized rotation angles that we get out of this. So this is how you're training the circuit, a simple circuit that I've shown. And this is how you're training the circuit using simple gradient descent optimizer. You can do Adam optimizer and all, it's all there. Now, what's the time? So it's almost 2. I think I'll quickly show you this. I have done it in Colab. So no, not this. Not this either. I'm going to quickly show you this. This is the, I don't think this will be running again, but I've done this. There is some error going on, df.head. I'm going to show you a data set, a medical data set. This is the data set. You can see it's on the heart disease. So there are age, sex, chest pain type, resting BP, cholesterol, fasting. All of these are features. And this is the outcome, the output, 0 and 1. So this is what you have. I'm not going to run this because we don't have time. I'm already running short of time. I'm doing this label encoder type of thing. Again, there are many categorical variables, as you can see. So I'm doing this label encoding. I think this is already label encoded. So maybe this is not coming again. So this is because this is already done. And I'm removing these features from my data set. Y is my heart disease. That is my column. This is my transforming my data set. That is, I want to standardize or normalize my data set. So I'm doing a test train split. So I want to validate my result. And this is the logistic regression. That is the classical machine learning, usual classical machine learning algorithm, logistic regression. My test score is 0.88. That is coming out to be 0.88. That is my test score. Now I am doing it on PennyLane. So this is my PennyLane. You can see my PennyLane now. Very important thing. Please understand this PennyLane, y, you need to first transform y into 2y minus 1, 2 into y minus 1. Because remember, your output values are not 0 and 1. In quantum circuit, your output values are 1 and minus 1. So you have to transform it in some way. So your 1 will remain as 1 and your 0 will become minus 1. Look at this. If y is equals to 1, your new y will also be 1. And if your y is 0, your new y will be minus 1. So this is the transformation to be done. Again, a test train split for PennyLane. Now, how many features am I using? If you look at the data set, some of the features I have omitted. I'm using 8 features. So there are 8 qubits I'm using. And this is the QML.device. That is, again, I told you, we need to attach the device, the circuit to the device. And this is my circuit. Number of layers is 1. What is number of layers in this case? Number of layers is how many times do I want to repeat my circuit? So I can repeat my circuit several times. So how many times do I want to repeat my circuit? I want to repeat my circuit only once. So this is what I have. So if I run all of this, again, it will take time. In a quantum simulator, it will take time. See, it has taken time. And the final test accuracy is lower than very much lower than the classical one. PennyLane, the circuit that I've made is giving 56% test accuracy, whereas in classical algorithms, it was giving around 88. Now I've done it in Qiskit also. This is the Qiskit one. I won't be able to run and show you again. So the optimizer that I'm using is Kobila optimizer in Qiskit. Kobila is a non-gradient optimizer. And you can see, again, these are hyperparameters that we can tweak. The maximum iteration, 20. Again, we can change this 20, but I've done 20. Again, you can see the reps is 3. Reps is how many times the repetition of your variational circuit do you want? How many repetitions do you want? If you keep on repeating things, your circuit is going to become very much complex. So it can model very complex relationships. So this time it is 3. And if I do this, you can see the test data set, my quantum variational classifier is giving me accuracy of 0.85, whereas on training, it is giving me lower 0.78, but on test, it is giving me 0.85. So again, we can tweak these hyperparameters and check. So it is coming very close to the classical data set. So, so the point is that it is not always that quantum machine learning will give you better results. Again, there are many things here you can tweak. You can change the number of the parameters that you are using. You can repeat these steps, or you can do many C0 operations. You can entangle, more entanglement you can do. So many, again, superpositions, many things that you can do to this circuit and make the circuit very complex so as to model the input output feature mapping. If it so model that very accurately. So the important point to note in quantum machine learning is it is said in quantum machine learning that as the data set is growing and as the complexity of the problem is growing, let's say weather patterns, predicting weather patterns is a very, very difficult task. Again, it's a very complex dynamics that is going on. Let us say personalized drug care. a drug therapy. A particular person might be suited for a particular drug, and that drug might not work in a different person. So genomics, these are very, very complicated areas where the output and the input features have a very complicated relationship. And it is said that quantum computing or quantum machine learning will be able to model these complicated relationships much better than classical machine learning algorithms, because of these two very, very important things, and that is superposition and entanglement. So if you make the circuit more and more complex, it can mimic those real world examples. But there is again another possibility of overfitting. So if you make it might happen in quantum computers also. So if you make the circuit more and more complicated, it might overfit, might not perform well for the test data. But that's again area of research. Very much research is going on in these areas. So I think I have shown what I wanted to. Just to check, let me check. I wish I could run that program in my Google Colab and show you. Okay. So here are some references. There is a very good book on quantum computation and information by Michael Nielsen and Isaac Chuang. You can go to the IBM website, IBM Quantum website, and you can learn from there. Very well documented. And PennyLane, again, you can go and learn from there. And these are some of the libraries that you can work in Jupyter Notebook or in PyCharm or whatever the IDEs that you have. You can work with these. These are the quantum machine learning libraries. I have used here Qiskit. In my talk, I have used Qiskit and PennyLane. Circ is by Google. You can use it. They are all good, but you can use it. And recently, we all know that India has also launched its first quantum computer, QPi AI, with 25 qubits, and DRDO and Government of India is spending a lot in quantum information technology. They have created a hub. Google and again Microsoft. I think Microsoft, you have Majorana as the latest quantum computer, quantum chip with 256 qubits, I think. And again, India is also planning to enhance it to 300 qubits from 25 within 2028. So it is going to be a big leap forward. So I think thank you all for patient listening. Thank you. Yes, somebody has raised hands.
Yes, any questions from the audience, please?